Okay, the recording has started. I will make it available to you in the announcements on Canvas once the class is over. So I'm going to go ahead and share my screen. So here we are at the course homepage. For those of you who didn't join in on our meeting last Wednesday, I'm Dr. Zenon. This is the Physical Science 1010 lecture class for our section S02, which means synchronous. We have weekly meetings on Monday and Wednesday from 2 to 3:15. And obviously you found the link somewhere, but I do post weekly reminders with the link to our meetings, and we'll be using Microsoft Teams for those meetings. And then after the class is over, I post a recording, and I do that in the announcements. So for today's announcement, I posted the link to today's meeting, and I posted the items that you have on your to-do list, basically, for this week. These are the assignments that you have to complete. And it reminds you that to find those actual assignment items, you have to click on the weekly overviews. Somebody has an open mic, please mute your mic. Thank you. We have a fairly large class, and sometimes bandwidth can be an issue if mics are open and videos are going. As much as I want to be able to have folk have their cameras on, I'm not going to mandate because we have such a large class. But again, every week I post the link for each class meeting, and I post the listing of the items that you have to complete for the week. And if you go into the weekly overviews, you can get to the actual assignment materials and items. So this week, one of the things that we'll take a look at is the project, so that I can give you access to the information that you'll need for the project. And, kind of get you started on that. And then we're going to also begin our first set of learning items dealing with measurement this week. And so you'll have to complete some items dealing with measurement by this Saturday. And just to remind you, especially for those folk who didn't join in last week, because I got a few emails over the weekend, make sure that when you are utilizing Canvas for this course, you want to make sure that you're using the RPCC login page to Canvas, and that is, it says RPCC Canvas, so that when you access Canvas, you're using the school's Canvas page. Otherwise, you might have some difficulty utilizing those items that are on the left menu. I got a couple of emails saying that this weekend, and I had to remind students that, if you're cross-enrolled at another school and you try to use that school's Canvas login page to get into Canvas, when you click on this class, because you will still see it available on your dashboard, you won't be able to utilize all of the left menu items properly. Also, I got a few emails from folk trying to use the Canvas app to do things. Be very careful with the Canvas app, because it doesn't always function the way we would like it to function. So I always suggest to students that utilize going straight into a browser. Chrome browser is typically best. Use the browser and go into Canvas that way, and make sure you're logged into the RPCC Canvas site for this course. Okay. So you did have some items to complete for this past Saturday, dealing with basically just, introducing yourself completing some items dealing with the course itself, getting yourself oriented. That was your task last week. For those of you who are just joining this week, you might have missed those items. I don't know, because you didn't join in our meetings where I covered that information. So I have to score those items, and I will be doing that here in the next couple of days to get the scores out on those items for you. Just to stay tuned. I'll get to them shortly. It usually takes me about a week to get everything for the prior week that you submitted scored and back to you, so that you can see your scores in the grade book. So just be patient with me. I'll get that done for you. All right. So now that should kind of, bring us up to speed on, what we've dealt with so far. If you have not, just a quick reminder, if you have not sent me the last page of your syllabus signed and dated, you need to get that to me ASAP, because one of the things I'll start to do here in the next day or so is to look at the emails that I've received and mark off those students have sent me what I've requested. And if you have not, then, then that means I got to start bothering you, hounding you about it, because that is a key piece of information that I like to maintain on file. Okay. All right. So before I jump into today's new material, anybody have any questions that they need to ask real quick? Just unmute your mic, ask away. All right, I'll take that silence as a no. No questions, meaning. And so let me go ahead and get into this material. So the goal of this week is to try to give you a basic introduction to science, start to focus on some of the key aspects of science, because all of that is relevant for the course that you're in, which is physical science, right? We'll look at the scientific method. We'll look at the connections between science and technology. And then we'll get into this idea of measurement and start to look at the idea of derived properties and derived units. And so we'll focus on kind of refamiliarizing yourself for those of you who might have done this, or for those of you who this is new to. We'll look at the SI base units and their prefixes and powers of 10. And so the goal here is to give you a little bit background and introduce you to the way we do things in science, and to begin our task of looking at measurement, because we'll see that measurement is key and critical to this physical science information that you're going to be dealing with. Okay. So I'll talk about the project on Wednesday. We'll table that for now because we've got today and Wednesday's class. And so I'll talk about the project. Probably what I'll do is, talk about it for about 15 minutes or so in our next meeting. So you'll have the information you need to get it started. You have to complete the measurement 1 discussion session by Saturday. That means you have to go in, click on this link, go in, answer the questions, post your answers, and then you have to respond to 2 of your classmates' answers. And the discussion forum instructions tell you that your posting should not be more than a simple "I like" or "I agree with your answers" or "we got the same thing," or but your response to your classmates should reflect a genuine effort to engage them regarding what information they have shared. Okay. And so, you know, they might post some information regarding a question, one of the questions that you did not think of. And so you will want to, you know, you'll want to engage them. The idea here is that since we are not face to face, this serves as our method of having a discussion. And so, you know, you will want to approach these questions as if you're having a discussion with your classmates, because that's what you would do if we were actually in class. Okay. All right. And again, your response and your replies to your classmates are due by this Saturday. Okay. So the other thing that I've made available to you is a set of readings and viewings. These are notes on related to this nature of science topic. Some of them deal with measurement because the introduction to measurement is something that we're also looking at this week. Typically the way that this works, so that I can explain this to you so you know how things are structured under this required readings viewing section. Typically the items on the top that say notes are portions of the textbook that I've made available to you, right? So what I did was, instead of just dumping the textbook in there and say, you know, read chapter 5, the notes from the textbook that are relevant for the topic that we're covering each week, I've put those notes directly in that weekly overview. So you don't have to go look in the book to find the notes that you need to cover, because I made them available here. I've also made some videos available to you in this section, required readings viewings, and some other items that can help you. The items on the bottom that typically say supplemental, those are the notes that I'm going to use to lecture. Okay. So the stuff on the top, so to speak, is typically what you will go through and formulate any questions that you might have. And then I will come back on top of the items that you're reading and watching and cover these. I call them supplemental notes. They're actually just my own personal notes. And if you watch the announcement for this class period, I'm going to add a link in the announcements. I will do that in each announcement posting where it's relevant. I will put a link to some additional notes that you can use to help study. So but only in announcements. I don't post them here for a variety of reasons, but I do make them available to you in the announcements. Okay. So that just kind of gives you a feel for how things are laid out. Because sometimes students ask me, where do I find the book for this class? Well, I've broken the book down by chapter and put it in the weekly overviews. I've provided videos that go with each topic in the weekly overviews. And then don't forget also, you have the useful links, which are some additional tools that you can use. And then in the announcements, I'm going to give you even more some additional access to stuff that can help you. All right. Any questions about that? All right. So I'm going to go into this nature of science notes. I think if I open it like this, we can all see it. Maybe not. Let's see. Something's going on with the Canvas viewer. So I'm just going to do it this way. Can all of you see these slides? Let me know if you're seeing this.
Yes, ma'am.
Yes, ma'am.
Okay,
Yes.
good. Because sometimes when I have to download something and share, I have to stop the share and then open that directly. But I'm glad you can see it. Okay, so especially since the Canvas viewer is acting a little temperamental right now. All right, so let me just kind of orient you to these notes that I'm going to be using. Okay. So basically, I give you some tips in each set of notes that I provide that I use as my lecture notes. Remember, they say supplemental. I kind of remind you on how, you can study, right? Students sometimes have a difficulty with this type of class knowing how to study. Okay. So there's some guidance here on how you can, I like to say, master this material. Okay. The other thing that I will say to you is, while you're following along, I know the tendency might be sometimes to tune me out, but what you need to be doing is jotting down information that'll help make this personal to you. These are my notes. If you want them to be your notes, then you have to do things in a way that will make them personal. Now, what some students do is they just print these things out. And if you want to do that, fine. You can do whatever you want with them. You can write on them, do whatever, right? Um, so, uh, you know, do your own diligence, in terms of words that you might not be familiar with, and making sure you understand that. And if you don't, you need to be asking questions, right? When I assign problems or give questions, you need to answer them. I make sure you have access to discuss things with your classmates. And then, when the time comes, you'll be doing you'll have an assessment, but you'll have problem sets, which are homeworks, basically, right? So if you went and looked at the syllabus, you see that each week you'll have a discussion, and then you'll have the following week, you'll turn in an assignment on that topic. So this week you'll do a discussion on the nature of science. Next week, you'll turn in a problem set on the nature of science, right? So I give you a bit time to digest all this stuff, and then the following week you turn in homework. I don't give weekly quizzes or anything like that, but I do give a midterm and a final. Okay, so just for those of you who looked at the syllabus, you know that, but just to try to help those people who might be trying to get their bearings about them in terms of how things will proceed in this class. All right. And so you can see that I've given you a set of objectives related to these notes. What are the main objectives of utilizing these notes? You should be able to utilize the scientific method and be able to discuss the connection between science and technology. Those are the main objectives that you should be able to, master as a result of going through this note packet. And I'm going to go through it with you, but again, you need to be making your own notes on this topic, right? So, one of the things we have to understand, since you're in a science class, is how did we develop the body of knowledge that we call physical science? Okay. So let's say, for example, if I had you purchase a physical science textbook, the question becomes, how did that stuff get in that book anyway? Why is that stuff in the book? Okay. And so one of the things you need to understand is, how do we amass the knowledge that we consider physical science? Well, so it tells you here that over the course of many centuries, curious people have used the framework of science to help reveal and describe this underlying order that nature exhibits, right? So, there are human beings who are very curious about how things work in our natural, physical, scratch and sniff environment. That's what you're here to do. You're here to do scratch and sniff science, physical science. How do things work in our physical environment? And so, over many, many centuries of human existence, people who have a curiosity about that have, done observations, investigations, and experiments to help us understand how nature works. Okay. And the people who have done these observations, experiments, and, um, have packaged the knowledge that they have in the form of theories and laws. Okay. And these theories and laws help to uh, express the things that we understand about our physical environment in the instance of physical science, right? I mean, there are other branches of science besides physical science. Okay. And for our purposes, physical science in this class is introductory physics. We don't do introductory chemistry in here. We do introductory physics. And so our task is for this week is to understand, how did those folk who were curious about nature go about uncovering the knowledge that we have right now. Okay. And then once they've uncovered that knowledge, how do they package it? How do they present it to the rest of the world? Okay. So it tells you here that, the knowledge that we have regarding our physical environment is packaged in the form of theories and laws. Okay. And so you see here, they've given, some listing of some of the areas of science, but our area is physics, right? We don't do biology, we don't do geology, we don't do astronomy. Well, we do a little bit sprinkling of astronomy. I won't say totally no astronomy, but chemistry, biology, geology. If you come see me in physical science too, we do a bit of geology. But in here, our bread and butter is really physics. Okay. And so what we're going to be looking at is those laws and theories and the knowledge that we've collected, that we label as physics. Okay. And so we can see here that physics is one of the most fundamental sciences. And so, physics endeavors to explain basic phenomena that we see happening in nature. So, how does energy work? What is it? Matter, space, and time. And how do they interact with each other? What's the connection between energy and matter? What's the connection between space and time? Physics looks into those things. Now, we're not going to be going into them at a deep level in here, because the goal is to introduce you to the basic concepts that form the body of knowledge that we call physics. And in fact, we'll be focusing on physics from a kind of a limited perspective, because we're going to look at physics that it can best be explained utilizing Newton's laws, for example. Okay. So it says, since physics deals with uncovering and understanding the fundamental aspects of nature, aspects of the universe, and I mean, there's a connection between physics and chemistry, physics and biology, and all those other disciplines. We have to, physicists do have to understand the laws that are relevant in those other branches of science. But, we'll keep it kind of straightforward here. For example, we're not going to be looking at atomic and molecular theories and laws that would branch chemistry and physics. We're not going to get that deep. Okay. But there is a connection. All right. So our goal here is, how do scientists go about uncovering knowledge, and then how do they go about finding ways to use that knowledge? Okay. And so, and as it pertains to physics. Okay. So here we go with this idea of technology, right? So I always like to use this example to kind of drive this idea home. So if you look at a telescope from 1500 versus a telescope today, they are very different. They are very different. And the telescopes of 1500 were built utilizing the knowledge that people had of optics and light back in 1500. Whatever were the fundamental laws of physics that they understood back then. But because our knowledge has grown, we've been able to develop more sophisticated telescopes. So now, because we understand things like, electricity and magnetism and engineering, and um, we have a better understanding of light and all kinds of knowledge that we didn't have back in 1500. We have built way more sophisticated telescopes. The other thing I like to look at, perspective that I like to use to kind of drive that idea home is, well, our telescopes of 1500 would only reveal certain things about our physical universe. But the more knowledge we gained about developing better telescopes, the more knowledge we gained about what our physical universe, the more knowledge we gained about our physical universe. In other words, we can look out way further into the history of our universe now than we could back in 1500. Back in 1500, the telescope led some to believe, most I should say, most to believe that the Earth was at the center of everything. But the better and better our telescopes got, and the more and more knowledge we gained regarding the physical environment, the more folks started to realize, hey, we're not the center of everything. In fact, the sun is the center of our solar system. And now we have telescopes that are so sophisticated that we have now had to totally revamp our understanding of our physical environment to say what? That is not just our solar system, not just our galaxy. There are billions of galaxies in our universe, right? So the more knowledge we get, the better technology we build. And the better our technology gets, the more our knowledge increases. So they're like in this, intertwined relationship. Okay. And so, another simple example of that, they kind of mentioned this idea of heating and cooling. Well, back in the day, there was somebody standing up with a palm tree branch fanning the king. Now you don't have to be a king to have heating and have cooling mechanisms in the summer, right? You just come in and turn it on, right? So again, the more knowledge we get, the more sophisticated our technology gets, right? And the whole goal of that technology is, in some sense, what? To try to make things easier or better, or at least that's supposed to be what it's about, right? I mean, I always tell folk that science is no different from any other human endeavor, and that is because human beings do science. And so all of the issues that plague the human condition plague science. Because, I mean, you can look in the history of our scientific knowledge and see instances where folk didn't use that knowledge the best way, or in an ethical way, or even in a humane way, right? I always, I like to utilize the idea of the atomic bomb, for example. Well, it took a whole lot of, it took a while for us as human beings to really get an understanding of the atom. and how, and how it's structured and how it works, the energy associated with the atom, and so on and so forth. And then we turn around and use it to build a bomb, something that could potentially annihilate the human race, right? So that you have to ask yourself, well, was that really the best or smartest use of our knowledge at that point? Maybe not. Um, so, you know, we over time we say that what science is this self-correcting mechanism, right? When we follow this, when we go through the scientific endeavor, over time, our understanding will become better and we'll have to weed out laws and theories that don't give an accurate or full description. One of the things you have to understand in this scientific process of gaining knowledge and finding ways to use that knowledge is we package that knowledge in the form of laws and theories, but neither of them is set in stone. If we uncover new knowledge that refutes those laws and theories, then we have to, you know, move in a way to accept the better explanations of how our physical environment works. Okay. So, I always tell students, you paid your money to take this class to see what are the most recent and current explanations. I said most recent and current and accepted explanations of how our physical scratch and sniff environment works as it pertains to physics at an introductory level. Okay. So that's what you're here to do. All right. And so they tell you here, as I mentioned, the cornerstone to, developing an ever increasing understanding or ever improving understanding of our physical environment is the observation. The key to that is people who are curious continuing to do observations on how our universe works. Okay. And then from that set of observations, that leads to investigations through in the form of experiments that allow us to refine our knowledge. Okay. All right. So scientific models, theories, and laws. So this scientific model is a way of simplifying something that is complex. Okay. So to give the example of the atom, which I mentioned a moment ago. Well, we can't, I mean, it took a while to get an accurate understanding of how the atom works, right? But we can simplify. I mean, the atom is a very complicated thing. It's a very complicated thing, but we can simplify that by looking at an atom as having electrons that move in planet-like orbits. Okay, we can simplify our understanding of the atom. We can even break it down and say, let's just use the idea of the atom having one electron to really simplify it, like as in the Bohr model of the atom, right? And then, but we know that once we move beyond one electron, things get a little bit more complicated. But to get a basic understanding, we can use that simplified model to help us, right? Now, a theory. And so let me just try to refute what most people think a theory is, and that is we're guessing. We don't really know, we're guessing. When we say theory in science, we don't mean they're just guessing. A theory is a way of explaining the things we see in nature through experimentation that is reproducible. So we see people are doing experiments, investigating a particular phenomena, and those experiments yield information that is consistent. Okay, not just once, not just twice, but many times. And the idea is that the knowledge that we get from those experiments, we package in the form of a theory. So I like to tell students that a theory is a broad explanation because it encompasses testing many testing hypotheses from many different perspectives. So, for example, the Big Bang Theory. So that theory seeks to explain how our universe came into existence. And it's not just one observation or one experiment that we're relying on to help us explain that. There are many different experiments that have been repeated and verified, and we've looked at this phenomenon from a variety, many different perspectives. So you have chemists that are doing experiments related to the Big Bang. You have astronomers. You have physicists, of course. You have biologists. You have scientists from many different backgrounds that are conducting experiments related to this phenomena, and all of the evidence that they've uncovered regarding that phenomena is packaged as a theory. So it's not a guess. A guess means you don't have any evidence, you just think that. But if we're dealing with a scientific theory, there is evidence based on experimentation that is reproducible, that is supporting the thinking and the understanding surrounding this phenomena. Okay, so it's a broad explanation. Okay, not just we're guessing, but we don't really know. That's not how a theory in science works. Okay, so the knowledge that we're packaging regarding this phenomena comes from a variety of experiments. So there are many different hypotheses that have been tested. Okay. A scientific law, on the other hand, that describes a particular pattern. You see where the theory says what? Patterns. Notice that the law says what? Pattern. Okay. So the law is more singular in its focus. It's narrower. Okay. And notice that it is being supported by reproducible experiments, but the law seeks to explain a particular pattern in nature. And it can often be expressed in the form of a single equation. And they give the example of F equals ma. Well, that's a watered down version, the version that you will encounter here in several weeks, dealing with Newton's laws of motion. Okay. And notice what I just said, Newton's laws of motion. I didn't say Einstein's, I didn't say quantum mechanics, I said Newton's. Very, restricted in its focus. Now we can, of course, we can explain a lot of things with Newton's second law of motion, but there are some things that we cannot explain with Newton's second law of motion. Okay, so the scientific law has its limits, if you will. Okay, all right. So I typically like to think of a law as we're testing, we're doing experiments to investigate a singular pattern, whereas in a theory, we're looking for, that our experiments can explain multiple patterns because we're looking at it from a broad perspective. But notice, neither one of them encompass we're just guessing and don't know. Okay? You see what it says? Generally speaking, a law describes a single action, whereas a theory explains a group of related phenomena. Okay? All right. So we're going from a singular phenomena, a single phenomena to multiple phenomena. All right. That's very important to understand because in physical science, you will encounter this concept of laws and theories and models as a way of understanding our physical environment. Okay? How do scientists arrange or order the information or knowledge that they have? Now, another key thing that you need to understand, and before I leave this, I'll say it again. Okay. Theories and laws and models help us to understand our physical environment. And if we find new knowledge that refutes these laws, theories, and models, then we have to be open to changing them because none of this stuff is set in stone. Okay? Some students take the perspective, and even some science, some folk who should know better, take the perspective that this stuff is fixed. No, the body of knowledge that we call science, and in particular for this class, the body of knowledge that we call physical science, is open to change if we find more credible knowledge. Okay, that's key. All right. So the question then is, how do scientists go about this work? How do they go about the work of, investigating and finding new knowledge? Okay. We know how they package that knowledge, but how do they find the knowledge that they're going to put in the package? All right. So one of the key tools that's used to help uncover knowledge and find new ways to utilize that knowledge is the scientific method. I like to tell folk the scientific method is a problem-solving process customized for the kinds of investigations that we do in science. Okay. Now, does all of the knowledge that we have in science come through utilizing the scientific method? Not necessarily. We do have our share of aha moments in science, just like any other, any other process or any other understanding. Because what science just offers us a way of thinking about our environment. Now we'll get into that a little bit more here in a moment when we broach the topic of measurement. But what the scientific method does is give us an orderly way to conduct an investigation so that it increases the opportunity for reproducibility. Okay? Because that's one of the things we need to be able to do in science to feel confident that we're investigating and uncovering knowledge that gives an accurate depiction of our environment. So that means people have to be able to question and reproduce what we do. And the scientific method gives us an orderly way of conducting those observations and investigations, right? So it says that the scientific method typically starts with an observation. So, somebody notices, hey, every time we do this, this happens, or I wonder why that happened, and so there's this curiosity about how something works, or how to improve a process, just something that we want to know, and that question guides the research. Okay. And then notice what it says. Next, the scientist typically performs some research on the topic and then constructs a hypothesis. Okay. Notice that they didn't form the hypothesis out of thin air. They went and did some research on the topic. What do we currently know about this phenomenon? Okay. And based on what we know, and based on what we don't know, I'm going to formulate this hypothesis, which offers a way of testing our understanding. Okay. So it says what? Then the hypothesis performs one or more experiments in order to test the hypothesis. So that's what an experiment is, an organized procedure for testing a hypothesis. And a hypothesis is what we like to say a testable prediction. If you just make a prediction, then that doesn't necessarily make it a scientific hypothesis. Okay? The scientific hypothesis is one that is testable through experimentation. Okay? So we have to be careful about that, because we can guess, we can predict about a lot of things, but those predictions don't have to, or don't necessarily all the time lead themselves to being testable. But if it's science, it does. Okay. And so through experimentation, the scientist can either confirm or reject or discard that hypothesis altogether, right? And so if the scientist conducts an experiment and they confirm the hypothesis, then the rest of the scientific community can come in and scrutinize that and say, I don't agree with this, or I agree with this, or or utilize what that person has done as a guide and reproduce what was done. Okay. The idea here is that if we uncover something that we, in the process of conducting an experiment, one of the key questions we're going to ask is, does it conform to the evidence or information that we have? Okay. Does this new knowledge that you say you have uncovered, is it consistent with what we already understand? Or, do you have, if your experiment says, nah, your hypothesis was wrong, then the scientist has to ask questions. Well, did I do something wrong in the experiment? Or was this just a bad hypothesis in the first place? And I shouldn't say bad hypothesis, because truthfully, most of the time when scientists conduct experiments, their hypothesis is going to fail. Okay. And that should not be something that a scientist is afraid of. So it's not that it's a bad hypothesis. That's not a great word to use. It is that, well, maybe we need to tweak this and start the process over again. Okay. And formulate a new hypothesis. So the way that scientists conduct investigations is through utilizing the scientific method. A key element of the scientific method is the hypothesis, which is a testable prediction. And then a scientist will go through a process of experimenting to test that hypothesis. And then the question is, was the hypothesis correct and conform and consistent with the information that we have, or do we need to start all over again? So here is a set of steps that I will say, that these are the steps to the scientific method. Sometimes you see steps 4 and 5 kind of broken down in a little bit more detail, but that's okay. If you utilize these 6 steps, when you are practicing with the scientific method or on a quiz, or on a test, then that this will be more than sufficient. One of the things I want you to focus in on, though, is that scientists don't jump from a question directly to the hypothesis. They have to do some research. So we say that a hypothesis is a testable prediction, but you might have heard the hypothesis referred to as an educated guess. That education comes through researching the topic. Okay. So it's not just a guess, it's an educated guess. You have some information or knowledge that is guiding you to make the prediction or hypothesis that you do, and it is testable through experimentation. Okay. So I like to use this as my, my kind of tongue-in-cheek example of the scientific method, if you will. Okay. And so some scientist somewhere in the world has a question. They want to know, when the Titanic sank, what happened to the water level on the shore? Now, honestly and truthfully, I doubt if there's anybody really wanting to investigate this, but it's just it's just a fun kind of an example to kind of get into some of the nooks and crannies of the scientific method. Okay. And so then the person has to go and do some research. So they have to read and synthesize all the information that's available on the sinking of the Titanic. How big was the boat? How cold was the water? How big was the iceberg? All kinds of things that, did they have a hole in the boat? All kinds of things that you need to know if you're going to address this question. Okay. So now, based on the information that's available, the scientists will form a hypothesis. Well, one of these, right? One of these had to happen to the water. So based on the knowledge and information that the scientist has when they do their research, they're going to test one of these. Okay. And so then you have to formulate an experiment. How are you going to test this hypothesis? Because obviously you can't go back and resink the Titanic, right? But if you have enough resources, meaning money and time and, skill, you have enough resources, maybe you can build a boat that's just as big as the Titanic. Maybe, you can invest the time to, stay in the North Atlantic until the temperature and iceberg just perfectly match, the conditions that existed when the Titanic sank. Now, honestly, I doubt if you get people to get on that boat, but you have enough resources, so you might be able to use crash dummies or whatever, right? In other words, if you have enough resources, you can model that situation, really close to what happened when the Titanic sank, right? But if you have a limited budget and limited resources, will you be able to conduct an accurate or test that even resembles that scenario? So you see, this idea of testing hypothesis is not just it's not as simple as as the statement, right? Because obviously the test you conduct will influence the outcome you get, which will ultimately influence whether you interpret your hypothesis to be correct or not. Okay? Because the saying, garbage in, garbage out, right? So if sometimes when you reject your hypothesis, you have to ask yourself the question, well, did my hypothesis fail because my experiment was lousy in the first place? That also brings up something regarding this idea of ethics, right? Because I did mention earlier that science is done by people, and people have issues, and those issues, science is not devoid or divorced from those issues, right? So are you being truthful about the results that you got from your experiment? Are you being ethical? All right. Or are you faking or fudging the results so that the world would think that you have truly uncovered that knowledge and information, and it's credible? Okay. All of you have seen the commercials on TV. If you have taken Avandia and died, call, right? Well, the question you have to ask is, well, what happened with that experiment? Did they know that this stuff was going to kill people? And they're just not telling us. Or did they really truly not know? In any event, something went terribly wrong there, right? Okay. And so after you've conducted the experiment and tested your hypothesis, then you have to analyze the data to determine, what happened. And this data and analysis phase of the scientific method is where, some books will call steps 4 and 5, they will kind of blend them together. But in these steps 4 and 5, that's where the measurement business comes in regarding physical science. Okay. Because the knowledge that we currently have about our physical scratch and sniff universe was amassed through observation and measurement. And so we'll be looking at that in more detail. And then, of course, the conclusion. Was your hypothesis correct? Is further testing necessary? Those kinds of questions scientists have to be dealing with when going through the scientific method to help amass new knowledge or find ways to use the knowledge that we currently have. Okay. And so I give a little bit historical background regarding the historical roots of physics. You see, they say here what physics started out as this kind of philosophy, natural philosophy, understanding. And that philosophy, encompass posing questions about, a lot of it will involve the thinking about how our environment works. Okay. But then at some point we start to really start to get into this idea of verifying through experimentation. Okay. Not just thinking about it, but verifying through experimentation. Right. And so you can see here that, we typically associate our knowledge of physics with the Western, what they call, our Western or Greek philosophy, in terms of its origin, although the ancient Greeks also interacted with other cultures to help establish their understanding. So, you know, but we typically pick the Greek philosophers as the start of those who began questioning nature in a way that eventually led to observation and experimentation. And so then at the next phase, we move toward those individuals who started to formulate what we consider classical physics. And Galileo is one of the key individuals in that, you know, in that movement, if you will. And then Newton was his successor, and most of what you will be learning about in here is based on the work of Isaac Newton. And that is Newton's laws of motion, because one of the primary questions that you, one of the primary bodies of knowledge that you will be dealing with in here is, what do we currently understand about motion from a Newtonian perspective? In other words, what aspects of motion has Isaac Newton helped us to understand, and what does he say about it, and how do we utilize it? Okay. And then once, you know, and then after Newton, we start to move into what the area that we call modern physics. And that is where we start to see knowledge and information uncovered by folk like Albert Einstein and Niels Bohr, and then, you know, some other folk, but you won't be dealing with the knowledge that they've uncovered, what we call relativity and quantum mechanics, you know, high level chemistry, that kind of thing. We're going to stick to our good old classical Newtonian physics in here. But, you know, just to kind of get a historical sense of the body of knowledge that we call physics, you know, this kind of gives you kind of a little bit of a historical perspective on that. Okay. So the key thing here out of this is, what is the scientific method? Okay. The steps of the scientific method, utilizing the steps of the scientific method, and the connection between science and technology. Okay. And then on top of that, how do we package that knowledge in the form of laws, theories, and models? Okay. So I will end here and ask if you have any questions. Please don't hesitate to unmute your mic and ask. We have maybe about 10 minutes. I'm more than happy to address any questions that you have at this point. Okay, so I'm going to unshare my screen. If you have any questions, please don't hesitate. So on Wednesday, we'll do a quick and dirty review of these concepts, and then we'll start to move more into those concepts that are related to measurement that we're going to deal with this week. Okay. So if you don't have any questions for me, you're free to go. If you have a specific question that you want to ask me, hang around. I'll be more than happy to address it. And, you know, if you have something that's more of a personal nature, you know, and you want to have a one-on-one, I do have office hours, or you can shoot me an email.
Thank you. Have a nice day.
You do the same, Mr. Jackson.
Yes, ma'am. Have a good day.
You too.
Have a good day.
You do the same, Hunter. Alan Treese and Irving, do you have a question for me? Irving, do you have a question for me? Hello? I still have two people in the room, and I'm trying to find out if you have questions for me. All right. If you don't have any questions for me, I'm going to stop the recording.